Hello, hey everybody. Welcome to the second episode of the Stocks and Crypto SQL show. My name is 𝗥𝗲𝗹𝗲𝘃. I'm a developer advocate at Timescale, and today I have an awesome teammate here, Jônatas Paganini. Hey Jônatas, how are you doing?
Hello, hello. I'm great. Very happy to be here and very happy, especially to be talking about this episode. So, yeah.
Cool, awesome. So before we start, if you're watching the recording, there will be useful links in the description because we always put the video on YouTube as well, so you can always rewatch it. And so today's topic will be schemas, and specifically, what are some of your options you have when creating a schema for storing financial market data. And so Jônatas will lead the stream. And yeah, I will watch the comment section. So if anybody has questions throughout the stream, we can answer that. And so I will share your screen now, Jônatas, and take it away.
Okay. So, welcome everybody. And the idea is we talk a bit about what is real-time market data, especially because we are talking about high-frequency data. So let's start with the agenda. We are going to talk a bit of show what is the financial market data, how we can store this into hypertables, and then how we can go and create aggregated data like candlesticks. And then we can start comparing the hypertables query performance and see how it goes in different directions, comparing with regular non-hypertables, let's say, or with hypertables, and also with continuous aggregation, continuous aggregates. And then we are going to add some compression there and show how this compression exposes and improves the storage system. So that's the idea. If you have any question, let's see if we can also address it during the talk. So what's the market data? In the market data, you basically can imagine that old market pit. That's the place where people were asking or making offers about what they want to buy or sell at some specific price. So when someone asks like, I can buy this stock by 100, and then someone say, oh no, I sell it for 120, and then they are like fighting between these 20 points. And then when someone say, well, I can sell my stocks for 100, so it matches with the someone that wants to buy it and someone wants to sell, and this is the trade. So we have these three types of events, like bid, that is this offer, ask, that is the price that is established by the seller, and then we have also the trade, that is when the transaction occurs. So you can imagine, like, when people are making offers in the database, in the market, they are, for example, putting some stop loss or some stop gain. It's the same. It's like an offer there. So you are, and then you can imagine that, like, bid ask first can work in this depth of the market. So, for example, if we have like 100 people that want to sell something in the specific price that is very below, and then we have like a more high value of selling, and then you can think like someone can go and buy from the cheapest price to the highest price, and they can swallow some, let's say, bandwidth of the market. So that's very funny. It's hard to visualize if we don't have a way to visualize. It's just about numbers and bandwidth, bit in ranges. But that's what is flowing inside these numbers. So and how we can get access to this market data. So we have several vendors. Several people can officially redistribute this, and we are going to use the FinHub API. So FinHub is finhub.io. That's the address if you want to try. And here is a simple screenshot to show how easy it is to get like latest trades. That's exactly what we are going to cover today. We are not going to go into this market depth or like bid ask offers. So we are just going to come to the trades. That's the real transactions that are happening, because the bid ask is a very heavy volume. So if you want to subscribe to trading messages, you are going to subscribe just like for real trading. But when you have a market depth, you need to choose the depth. Like, oh, I would like to see like 5 prices up in my stack or 5 prices down, and then it makes very complex. Like people are, for example, moving their offers along the way, so you need to keep the track of this. And the objective here is more show how it behaves and how is to connect and keep it alive. So let's take a look in the details here. So we have this JSON event that is exactly the same from the previous page, and basically you come with price. S is from symbol, like this is like Bitcoin USD transaction, and then you have also the timestamp here, and you also have the volume. And then apart from the data, you have the type. So as you can see, a small detail in the data that it's an array, so you can receive several transactions in the same point, because from sometimes you are receiving like 10 events per second. Other times you are receiving like 600 events per second. So like the stream is a WebSocket, so it keeps flowing the data around. And here is the simple Python script that we built based on the previous one. So as you can see here, we have this on open that you can subscribe, and then we have like on message. So every message in the example is just printed. So we started with this and just change it to say, if the data type is trade, let's iterate under the data array and try to do on trade for every event. So on trade is just like splitting the time and creating a tuple with the with all the data. So it's using the price, the volume, and also the symbol as the parameters. And you can see in the top that we are just doing insert and time, symbol, price, and volume. And that's all. So it's very simple. We open a cursor, we execute this insert with these params, and that's all. How we are running it? We are like 2 weeks now collecting data from FinHub API, and we are just doing for a few different types. And I'm going to show you the DSL, the model. That there is no secret here. Like the time is a timestamp TZ, the symbol is a text, the price is a float for, and the volume is a float for data types. So this is how it's the base that is going on here. And then like as we have this very huge amount, we can also think about like aggregating this data. So this next step, I'm going to show this very simple query that is basically open, high, low, close plus volume 1 minute. And then we break down the time buckets into 1 minute, symbol, first price, max is the high vol, and I can call it high and low for price. We are not considering, and then we can also count the amount of events and also sum the volume to just say, well, in this minute we have several transactions. And the thing that is very important here is with TimescaleDB continuous, because when you call TimescaleDB continuous, you can simply watch it, and even being a materialized view, it will materialize the data only when it's ready. Let's say you need to close the time bucket to save it, so it can do it in this way. And we also create an continuous aggregated policy. So this one is like a background refresh that can go and keep, let's say, moving data. So I say like from last month of data to the last minute, just go and refresh this data on the materialized view. And it will keep refreshing every 1 minute. That's exactly what we want. So this is the basic of what we have done here. And now let's go and check it in action and understand how it works, and especially understand this data and how this stream is working. So the first thing that we are going to go over here is comparing the query performance. So the performance of the queries can vary a lot because the amount of records, and also depending on the statement of the query, how you are organizing your index and everything. And I'm going to just run some queries that are quite simple, and then we can compare the queries. So just to be clear about our context here, we are our context on fetching data is like we have 33 million records in most of the tables. I have some copy of the tables. In average, it's like 2 million records per day and 25 plus per second, just like Bitcoin and Ethereum. So this is like some numbers to keep in mind. What's our current hardware? We are using half CPU unit, and it's still like less than 5% of the CPU being used in the real to do these inserts. And we have a 2 gigs of memory, and this is like in average just using 40%, and we have like a 40% of 10 gigs, like 4 gigs being used in 2 weeks with no compression. And I also duplicated the table 3 times, so it's around like 1 gig, 1 gig and a half to have like these 30 million records. And the idea is just run the queries, and I will just come here now and show you what I have in mind. So the first thing is this query. I already showed this, like the query for creating the open high low close. So I will have this. This is a terminal that is running on the server. And if I say here table, oh, I was not connected. Huh. Yeah, this is okay. So if I call this, I get the bucket. Let me just order by desk. So this is exactly this last minute, and this is in progress. Like this is like you can see we have just 2 ticks here, 8 events, but like almost all the same price. And then you can see that this is like a changing over time, depending like how much data is coming through. So this is the candlestick of one specific candlestick of a specific moment, and this is like quite fast, like instantaneous and so on. So, but what is behind the scenes? Like, how can we get into there? So let's minimize this query to just get like the last price, that some price that is enough. So if we start with the trades one, so order by time task limit 1. So this is the last trade in the database. And then if I keep switching it, you can see like we are receiving a lot of ticks here, and this is changing often. And this is like live inserting, because we are in real time watching it, and we have like an EC2 instance running Ubuntu and running this Python script that I showed you in a background job. So it keep watching it all the time, and if the connection closes, it opens the connection, subscribes again, and keep doing this. And you can see that this is a lot of things going, and this never stops. So for example, if I do here, like for example, some count, just to show you order by time, I can just say order by time. No, I don't need the order by. I can just say where time is greater than now minus interval of 5 minutes, for example. So we have like almost 10,000 events in the last 5 minutes. So this is really flowing a lot of events, and then we need to be careful with how we are going to storage it, how we are going to manage this data, and especially count it. So 2 days ago, I was doing something here to see to see how it behaves, and this is what I'm going to use to compare. As you can see, count is not very easy to run. Like we spend a few seconds. I will start enabling timing now, so we can check how much time we are going to run everything. So we have 36 million records here in this trades table. And then what I did here, I have other tables. I have this trades 2 table, and I also have the trades day table. And both tables, they are like, this is a hypertable and this is a non-hypertable. The only difference is that these are not like live streaming. Trades are live streaming, and this is just a copy of the records from 2 days ago, and this is also a copy of the record. So they are not like exactly with the same number of records or anything, but you see that they diverge a lot. And the thing that is different here is that trades day here is using a different a chunk interval. So basically, when you run create hypertable, so for example, let me show where we are running here, hypertable. So I'm not saying here what's the chunk time interval, but I can say it. I can say something like chunk time interval, and then I can use some real interval here, like 1 day. And that's exactly what I did in this another table named trades day. So this is what I just a moment, because I think I have this in another file. Oh yeah. Yeah, so the trades 2 is here. This is the same. So just to show you this, and then we have also this trades pair. So this trades day, not trades pair, sorry. So if I call here \d trades, you can see that it shows that three tables, because it's weekly based. But if I call trades day here, you can see that it will have 14 14 child tables because it's generating one table per day. And we have like advantages and other things that are not very very good, but in general it's good to think about it and reason based on your business, based on your needs. There is no right or wrong, but you can optimize it for your needs. So think that if you have like for example, if you have a 30 million records in 3 chunks, it's 10 million records. So it's going to a table of 10 million records, while in this other case that you have 14 tables, it will just be like 2 million per table. So it will open the table fast, it will read the records, like how the records are put it all in memory, or like compress fast, decompress fast. But if you need to open too many of them, it will slow down because you also have this trade-off of opening, closing, compressing, decompressing, and so on. So it will depend on your need, and there is no right or wrong. So let's start running some query here that we can just try to see what we have. And so let's get some max price. Let's get only price. Let's get everything from trades ordered by time 1. Okay, so getting it from trades is very, very fast. And this is because the table trades is already partitioned. And if you see here trades 2, it's not partitioned. So it's just like a regular table. And you can see like from 161 milliseconds, it's now almost 6 seconds. So it's a lot more, and this is the issue that we have. If we try the same here for the other table, that's the trades day, the difference will not be too much because it's also partitioned there. So if you say here on the explain, you can see that it will use this custom schema. So what's the chunks that it should go through, while the other system will not. So this is a basic thing, but it really helps you to understand that where you go and how you can move this. So again, here, like I have this trades day, 2 seconds now, and if I go to trades, that is the other hyper table with just 3 subtables, so it's even faster. And if I go here and try trades 2, that's not a hyper table, I will see that it will be much slower. So as you can see, like the difference is huge, and this is more like the mindset of how these hypertables say here D and DT plus on trades 2. You can see that, oops, I just wanted D plus. And you can see that this is all the details, but if I call here for trades, for example, you see that we will have these child tables. And if I get some of these child tables and just describe this one, you see that it contains, for some reason, it's not running. It's stuck. I don't know why, but yeah. So what I would like to show here is that when you do this, you can, when you describe this table, you see that every single hyper table here has a constraint to not allow to insert data that does not belong to that chunk. And it's really fast and make things really parallelizable. And yeah, that's how how you can make more things here. So that's the beginning of the queries. I can also show more queries here. So the first query that I would like to continue is one thing that I was learning with Dave in the last Twitch episode, that is about window functions. So functions are quite cool because we can just name things and start really let's say understanding and shifting data and getting some data over our window function. So in this example, I'm just going to and this is running over open high low close of 1 minute. I'm sorry, I forgot to show the difference of running on open high low close of 1 minute as well. So let's do some real example of this 1 minute thing. So if I try here, if I try here time bucket 1 minute, I'm sorry about that. So I will get like to max of price as high, mean of price as low, and then I get like first price as open, last price as close. I think time the first and last because it needs to know what's the reference column to order, and then I get the last price based on time, and then I can assume volume here as volume. So, oops. Oh yes, I forgot to say grow by. Sorry. So I will also get the symbol because the symbol is quite. So let's get symbol first. Symbol, and then I can start grouping by this. So I not have the order by for now, group by. I love to use these options like that says 1, 2, 3, 4, 7. Okay. Yes. Six. Yeah. I think. Yeah, let me just confirm here because I diverge from this. So let me just copy here because so I'm saying 1 minute of time, first price, max min. Sorry, I missed the group by clause. Group by 1, 1, 2. Oops, typo. Okay, so now it's weird because it's going to run over everything, and it's too much for now. It's like 30 million records. So I need to say desk order by order 1 desk limit 10. So let's get the last 10 candlesticks from this, and then we will see how hard it is to process this, because like we are inserting a lot of data and then we are pre-processing, and this is trying to get it from the hypertable, but as you can see, this is quite heavy. Keep in mind that we are using a CPU machine, so this is like a fake thing. I can also show you this just to be clear that we are we are doing this, and then I can just I can show you that this is the machine, and how this is really working. So this is the FinHub. You can not see the full host or matter, and as you can see, this is like the 40%, as I mentioned, because we have 3 hyper tables. But you can go to metrics here, and we can see like how much of the memory we are using. Sometimes we are almost reaching the memory and everything, but this is a very, very small machine to start, and that's how we are running it. So sometimes it's not that fast. Oh, I can't believe I missed to hit enter for some reason. When I hit enter, it was, oh no, it was like really 1 minute and 29 seconds to run. So as you can see, it's almost impossible to get this data in real time, and that's why we are using this aggregation. So the aggregation comes to just solve this. So as you can see here in the aggregation function, what we are doing is we are using this query, but every time we do some insert, it will keep refreshing the data for us. So it will refresh the materialize the view, and split the query, and process the data that is missing directly from the table only when it's necessary. So if we ask like for 10 minutes or something, it will be quite fast. Okay, so cool. So we are building this dynamically, and so if we get exactly the same, like the 1 minute order by bucket, desk limit 10, and then we can see that it's like half second. So instead of 1 minute. And then like if we try this, like exactly this on this, for example, trades 2, that is the other table that we have, maybe it will be less or more than the regular hyper table, but this is not the case. What we want to emphasize here is like probably when you reach some granularity level, you will not end up with this granularity forever. So you will use it to process your data, to collect your aggregation of data that you can do in sites. And if you want to continue using this, maybe you will compress this data to be easily accessible later, but with less storage. And then let's jump into this topic now. So the idea here, we compared the query performance, and now it's time to enable compression. So I already enable compression, and I'm really sorry. There is a typo here. The compression policy is running over trades table and not here. And the idea is more like showing compression in action. So we can see how much data we have. So sharing a bit of the storage details. We have the trades table. This is with the real-time data. This is growing all the time, 2 million records per day. And then we have the trades 2, that is the table with the copy of 30 million tables. It's non-hyper table. And we also have this 30 table that's 30 million trades. So what we are going to do now is just collect the data around it, and understand how much data we have, and how much bytes we are using for every single case. So let's start with the these queries. I already prepared some queries because this topic is quite complex. When you have like a regular Postgres relation, you have a way to get this data from there. But for hypertables, we split the tables in subtables, and it's not fully compatible with the PG catalog. So we also provide functions that you can understand what's the chunk state and so on. So when we call chunk, we know that we have a chunk, but if we don't have a compression policy, it's not like with like a status, so we don't know if this will be compressed or not. So as you can see, there is some extra code here, like we are using like a chunk compression stats and also chunk detailed size as outer join to get these extra details. So for example, if something is compressed or not, we can get all this information from these chunks with compression. So let's take a look at this table. So you can see here like trades, and then we have like before and after compression bytes, and this is basically what we are going to explore. So this is a bit boring to be using this all the time, so I will just copy this query because a few PG pretty size pretty here. So as you can see, like I'm using like this to just show the megabytes, and also I'm getting like some formula here to check the percentage status. So if the before compression status is okay, I will use it. Otherwise, oops, I have an issue in this query. And what's the idea here is sorry, let me just move fast here. Okay, after compression status. So what I'm calling here is just a formula to see the compression ratio. So if this is not compressed, it will be null. So if this come null, I will just reuse the value to just divide by 1. So that's the idea. And then is, oops, no, that's not a query. Okay, so let me just check it again, and let's see. Let's use as it is just to confirm. But yeah, you can see here that it contains like it's saving 88% of the size. So you can see this is the before and the after. So when it's uncompressed, it's like 164 megabytes, and compressed, it's 18. It's a quite huge amount of data that you can save. So for example, like we can just say here, let me edit this query, because we can say sum of total bytes and sum of after total bytes, and forget about the compression ratio, and let's just run this. And then we can see that we have like 40 gigs, and then we now have like less than 10% used. So it's quite cool and quite interesting to see these, and the queries performs well. And for looking the table that is, I'm sorry, we have an error here. Let's just make sure we don't overcome this. So where hypertable name equal trades. So let's just make it for trades, because we also have the trades day. That's another table. So, and you can see here that it's like 2 gigabytes, and then we have 113. So we have more before, because we also have the other table that is the trades underscore day, that is just 30 million records, and it's very similar. but you can see that with a different chunk size interval. So for example, this has a bit less data, but with more chunks, it ends up with more data because you have also less data to compress. So the compute is a bit worse in this case. And this is not a big deal, like it's still a lot, but this is just like for comparison, for the sake of understanding this. And what else we have here? So we need to check for the catalog thing. I think I have this query here. Nope. I need to search on Google. Just a minute. Table size post increases care. So yes. So this select, and here we can call trades true. So you can see that this is still there. It's still like 1.8 gigs. So this is a bit smaller than the previous records here, you can see, but this is not the case. Like we are getting faster queries, so you have the downsides and the trade-off to mix it. And yeah, so this is the basics of what we want to show today about this difference between these schemas and how much stock can save, and especially how it can help you to design your system. I was using the chunk size of 1 day versus 7 days, and maybe they will work better with compression, but not for long periods of queries. So it will all depend on your setup, and the best thing is just to go and try this out and test and optimize for your case. Into our website, we have a few best practices that you can also choose. For example, we always say that the chunk size should be less, like all the chunk size that should be on memory for time, they should fit into like 25% of the memory, so it will allow this flexibility. But maybe this is also like a range that you can see what fits better into your business. And this is the basics of how you can measure. I was compressing all the chunks from the previous. For example, in this case here, if we check like, let me get this chunks with compression. So you can see that some of them are still new. In this trades day, but most part of the chunks are compressed, and on trades not, because the actual data is being inserted into a chunk, so it's impossible to be compressing. In this case, this is the one, because it does not compress before or after, so it's still in progress. And yeah, so that's what I would like to show. So if you have any questions, we can try to address now. Otherwise, thank you very much. So let me jump into the live stream.
Thank you, Jônatas. I don't see any questions, but if anyone has questions in the future, you can join the Timescale Slack community, slack.timescale.com. Jônatas is there. I'm there. Also, a lot of other Timescale team members and TimescaleDB users in the community. So that's a really good place for everyone to learn more about TimescaleDB and ask questions. Also, just to put the link for the documentation, docs.timescale.com. We have a lot of interesting tutorials to get started with TimescaleDB, we also have multiple tutorials that cover crypto and stock data. And also we are hiring. So if you are interested in joining Timescale, and we are pretty much hiring in, I think, all of our departments: engineering, developer advocacy, marketing. So go to timescale.com/careers if you're interested in that. Yeah, I think we're wrapping up. Thank you, Jônatas, again for your presentation.
Thank you.
Cool. And see everyone in our next stream. Bye.
Bye.